Hello everyone, my name is Anjali Upadhyay and today I'll be explaining the concept of optimization of loss function and the best line fit using gradient descent. Let's talk about what regression really means. Regression is basically a method that helps us find the relationship between two or more variables. For example, if we know someone's years of experience, we can use regression to predict their salary. The main idea is to draw a line that best represents the pattern or trend in the data, and the line is what we call the best fit line. The equation for this line is very simple. Y is equal to mx plus c. Y is the predicted output, and x is the input variable, m is the slope, and c is the intercept. Our goal is to find the best values of m and c, so that our line fits the data as closely as possible. So what does best fit mean? How do we know which line is the best? Best fit line is one where the predicted values are as close as possible to the actual data points. The difference between actual and predicted values is called error or residual. So our job is to minimize these errors, and to do that we need something called a loss function. A loss function. Sorry, the loss function, also known as the cost function, measures how bad our predictions are. The most common one used in linear regression is the mean squared error, or MSE. The formula looks like shown on the slide. L is equal to 1 by n summation of y of I minus y of I cap the whole square. It basically takes the square of each error, adds them up, and divides it by the number of data points. Our target is to make this loss as small as possible. That's how we know our line fits well. Why optimization is needed? Let's say we pick some random values for M and C. The line will probably miss the data completely, meaning our loss will be huge. So we need a method to adjust M and C intelligently, step by step, to reduce that loss. That process, the mathematical way of finding those perfect values, is called optimization. And one of the most popular optimization techniques is gradient descent. So, what exactly is gradient descent? Imagine you're standing on top of a mountain and you want to reach the lowest point in the valley, but it's foggy and you can't see far. You take one small step downhill, check if you're going lower, and keep moving in that direction until you can't go any lower. That's exactly what gradient descent does. It takes small steps in the direction of decreasing loss until it reaches the minimum point. Each step adjusts a slope m and intercept c slightly to reduce error. Now, to understand what how gradient descent actually decides which direction to move, we use a concept from calculus, derivatives. The derivative simply tells us how much the loss function changes when we slightly change a parameter, like m or c. Think of it this way. If the slope of curve is steep, it means we're far from the minimum and need to take a bigger step. But if the slope is gentle or almost flat, it means we're getting close to the minimum and we should slow down our steps. Mathematically, we calculate the following partial derivatives as shown on the screen. These derivatives show the direction and magnitude of change in loss for both parameters. If del L by del M is positive, it means increasing M will increase loss, so we move in the opposite direction. If it's negative, it means increasing M will actually reduce the loss, so we adjust accordingly. This is how gradient descent learns, by constantly checking out how much loss changes for each small tweak to M and C. In simple terms, derivatives are our sense of direction, helping us find the path downhill towards the lowest loss. Let's now look at the full algorithm step by step so you can visualize how everything works together. Step 1. We start by initializing our parameters M and C randomly, because at the beginning, the model has no clue where to start. Step 2. Using these values, we predict y for all our data points using the equation y is equal to mx plus c. Step 3. We calculate how far our predictions are from the actual values. That's a loss. Step 4. We compute the gradients, which are the partial derivatives we just discussed. These gradients tell us how much and in which direction we need to adjust our parameters. Step 5. We update M and C using the update rules. Here alpha is the learning rate which decides how big or small our steps are. Step 6. We repeat this process hundreds or even thousands of times until the loss becomes very small or stops changing significantly. When that happens, we say that our model has converged, meaning it has found the best possible values for M and C. You can imagine it like training the model, keeps practicing and adjusting itself until it becomes as accurate as possible. Every repetition makes it slightly smarter, and that's exactly what machine learning means, learning from errors. What Now let's visualize this concept, because gradient descent becomes very clear once you see it as a movement on a curve. Picture the loss function as a curved surface shaped like a bowl. The lowest part of the bowl represents the minimum loss, and the sides represent higher losses. The algorithm starts somewhere on this surface, maybe far away from the bottom, and takes small steps in the direction of the steepest descent, guided by gradients. With each step, um, the loss decreases. So you can imagine a ball rolling down the bowl slowly towards the center. The learning rate plays a very important role here. If it's too small, the ball rolls down extremely slowly. It'll take forever to reach the bottom. If it's too large, the ball might overshoot the bottom and bounce around forever, never settling. So, finding a good learning rate is crucial for smooth conversion. When plotted on a graph, you'll see the loss value dropping sharply in the beginning and then flattening out as it approaches the minimum. Example, let's take, um, suppose we have a data set of years of experience of and versus salary of group of employees. Initially, a model might guess um, some random values for MNC, maybe a very steep line or a completely flat one, and obviously that line won't fit the data points well. When we calculate the mean squared error for that line, we'll get a large value, meaning our predictions are way off. Now we apply gradient descent. After the first few iterations, the lines start adjusting. Maybe the slope decreases slightly or the intercept shifts up or down. As the algorithm keeps learning, the line gradually positions itself in such a way that it passes as close as possible to all the data points. After several iterations, let's say 500 or 1000, the loss becomes minimal and the line barely changes anymore. That's the optimal line. Our model has found the perfect MNC that minimizes the overall error. So, To wrap it up, we started with the concept of regression, where we try to fit a line through the data points to predict continuous values. Then we discussed the loss function, which measures how far off our predictions are. The higher the loss, the worse a model is performing. Then we talked about optimization, the heart of machine learning, uh, and that's where gradient descent plays a key role. Gradient descent continuously adjusts the model's parameters, learning from the errors, and keeps improving until it finds a sweet spot where loss is at its minimum. The result is the best fit line, which represents the most accurate relationship between the variables. What's beautiful about gradient descent is that it's not limited to linear regression. It's the foundation of almost every modern AI model. Neural networks, deep learning, and even complex LLMs like ChatGPT all rely on gradient descent, just with millions of parameters instead of two. So, by understanding the simple concept, you're actually understanding the core principle behind how machines learn. In short, gradient descent is not just an algorithm, it's the brain of learning systems. Thank you.